Oh, Bayes, who are you? Why does the whole world think you're naive? Well, that's the question we're going to answer in this lecture. Naive Bayes is the second learning algorithm we're going to talk about. It is somewhat simple, similar to logistic regression in terms of its complexity. And the main difference with logistic regression is that nobody uses naive Bayes for anything ever. Nothing. Maybe baselines, something along those lines. But naive Bayes is still a very important machine learning algorithm, and it's a great introduction to an important other way of looking at machine learning besides what we've been talking about this whole way through the lecture so far. And so it's worth taking a lecture, learning about this point of view, although we won't be implementing or using naive Bayes. We've talked about the different ways of slicing up the machine learning algorithm space and problem space. And we had supervised, unsupervised, semi-supervised, and reinforcement learning. But of course, each of those things can be subdivided a billion times on and on and on forever. And one very important subdivision is the difference between discriminative and generative modeling. Now, everything that we've been doing so far is discriminative modeling. And that is, we model essentially the probability of the label given the features directly. That is, the model, it's like the model is a function that takes in the X and outputs its prediction of the Y. Now, the techniques for that are logistic regression, decision trees, neural networks, the ensembles, which I mentioned as an important kind of extension to the decision tree space. The main toolkit of things that people use are discriminative algorithms. The other approach that you could consider is generative algorithms. And in a generative algorithm, you would model the joint probability of X and Y occurring simultaneously. That is, you would model, for example, in the spam space, what's the probability of a certain feature existing along with another feature, along with another set of features, along with Y, et cetera, et cetera, et cetera. And you'd model all of that, and basically, in some sense, have a deeper understanding of the world and the way the world works than you would need for a discriminative model. And then there's this tool called Bayes' rule, Bayes' theorem, which we're going to spend some time on in this lecture. And you can use Bayes' rule to extract the discriminative property that you want from the joint model. You could also extract many, many other things once you have this underlying generative probabilistic model. So that's the kind of like philosophical split between discriminative and generative. And you will hear of important, often talked about generative techniques like naive Bayes, Bayesian networks, hidden Markov models. And I would say that these are certainly not unused in practice, but probably less used in practice than the discriminative techniques. And if you are interested in that, here's a paper in very, very hard to read font from where I am, but hopefully you'll be able to read that if you want it, which talks about sort of the pros and cons of them. And, leaving kind of like the script and talking more about my personal take, I feel like these generative techniques are often more focused on probabilities and being fundamentally correct in an underlying way and being very principled, and they tend to be a little bit more math-heavy approaches, whereas often discriminative techniques are kind of like a tree, like a bunch of if statements or something along those lines is what you end up with at the end. And that's, maybe a fast and loose, sloppy way of saying it, but another big difference is that discriminative techniques really don't waste any modeling time, any modeling effort, any parameter sweeping effort doing things that they don't need to do. They focus on their task. We gotta deal with why. Whereas a generative model, you might go and spend a lot of time learning all subtle interactions that in practice don't help you with the problem you're trying to solve. So a generative model would be more useful when you are going to take an extended dive into a particular domain where you're going to be pulling out lots of problems from the domain and not just be very focused on here's a particular thing I'm trying to do. And I'd say from my personal experience, it's been like 100% on this side of the world. I mean, I wrote a paper about this when I was in grad school, but really the other side of the world. Okay, there you go. That said, it's still, naive Bayes is still a very important algorithm, and generative models are still very important, and there are very, very smart people who are generative first thinkers. And in fact, I'd say maybe some big breakthroughs on the discriminative side have come from people who thought about the problems in a generative way. So there you go. It's an important part of machine learning, and we're going to spend a little time on it. But before we get there, we do need a little bit of probability. So I'm going to introduce some basic probability concepts, walk you through an example of using Bayes' theorem. Then I'm going to present the naive Bayes algorithm and an example of that. So probability concepts. Right here, what I've drawn is an instance space with two variables, x1, x2. And in the past, we've drawn our linear models on this, like, okay, that's a separator in the instance space. Everything on one side is classified as one way, everything on the other side is classified as another way. So that's pretty much the same thing we're showing here, a two-dimensional instance space. Now, you could say that there is an event that can occur, and mapping this to the concepts we've talked about before, this is kind of like y equals 1, or you could say in this region, a equals 1. So the event's name is A. The probability of A being 1 is 20. And so we've drawn this circle to be about 0.2 area. The full space is an area of 1. This space is drawn to scale as possible to be to have an area of 0.2, just to help you sort of visualize things and how they interact. Then you can take a sample point and just arbitrarily draw from the underlying distribution. Here's a point in the universe, and you can ask some questions about that point. Is that point A or not A? And now if the point is here, where it is outside of that circle we've drawn as A, you would say that point is not a point. But if the circle were instead at this other location, and you can see my PowerPoint animation skills are like, psh, 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 then you would say that point is A. Kind of like, you could think of this as y equals 0, y equals 1, whatever. But this is just a way to visualize that and some interaction. And the reason that you'd want to do this is when you start getting into more sophisticated modeling of probability spaces and interaction between the variables that make up the probabilistic model that you're creating. Because you can have a second event, and here we'd say probability of B is 0.1 or 10%. Now, B and A are drawn in this space in a way that allows us to see how they relate to each other. So you could ask questions like, what's the probability of A and B occurring? So what does that mean? That means you draw a point at random, and what's the probability that point you've drawn is both in A and in B? And I'm sure probably this math, you've seen this 100 times, this is second nature to you, but we're just reviewing a few things here, and you can see that probability is 0 because A and B don't overlap. So you cannot pick a point in this instance space that is in both A and B. Another question you could ask is, what's the probability of either event, A or B? And that one is actually a thing. And if you look at this for a second, and there's PA, PB, you would say that the probability of A or B is 0.3, because if you pick a point at random, there's a 0.2 chance it's in A and a 0.1 chance it's in B, and there's no overlap, so you can just add those things up. Then there's this other notion, which is conditional events. That is, what this says is the probability that the point is in A, given that the point is in B. So one way to think about that is that you sample a point in B, not in the full instance space, but you just draw a sample from B. And what's the probability that point that you've sampled randomly from among the options in B is also in A? And of course, we got a 0. But don't worry, we're going to get better than 0, because now we can add a third event and call it C. So now we're getting some interactions and some interest going on. So let's ask these similar questions again. What's the probability of A and C? And now there's not enough information here to calculate it exactly, and you kind of have to eyeball it, and you have to say, well, about half of C is in A, and C is 0.1, so about a half of 0.1 overlaps A. So that means that the size of this right here, which is A and C, is about 0.05. And so you'd say, well, the probability of picking a random event and having it appear in those two things simultaneously is 0.05. The next thing you might want to say is, well, what's the probability of A or C? And that would be, this probability, like I don't, there you go, that probability. And that is, A is 0.2, C is 0.1, but half of C overlaps with A, so you only get to add on that 0.5, so it'd be 0.25. There you go. If I went a little fast, pause it, take your time. Or if I'm going too slow, I'm sorry, get used to it. And then here's another thing you could ask is, what's the probability that the event is in A given that you know it's in C? So I will get my head out of the way there. And what you would say now is that you sample a point uniformly from somewhere within C. And what's the chance that that point that you sample from within C is also within A? The answer to that is, of course, 0.5, based on the fact that in our eyeball sense, we had basically said that half of C is in A. So, half of the instance space of C, when you sample from that, you get also A, half you get not A. And then you could turn it around and say, well, what's the probability of C given that you've sampled in A? So you pick a sample in A, and what's the probability it hits in C? Now, this is a little bit trickier. The probability of A and C is 0.05. Probability of A is 0.2. So A and C covers about 25% of A. And so just with that eyeball thought process, you would say that the probability of C given A is 0.25, because if you pick something in A, it's going to be about, 25% of the time it'll also be in C. And maybe that revealed my inability to draw circles to scale, because that doesn't quite look right to me, but that's how the thought process would go to figure that out. So that's a conceptual description of some basic things about probability. You can turn those into rules. And so here's a rule of probability, which is the product rule is what it's called. And that is the probability of A and B equals the probability of B given A times the probability of B. And that was sort of the thought process we just went through to get here. And it's symmetrical, so you can do it in both directions. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B, because you don't want to double count that region in the middle. And so this works if they're not overlapping. This A and B would be 0, so that would work fine. And another thing that you're going to need to understand the next slide and the exposition of the Bayes' theorem stuff is this called the theorem of total probability. And what this basically says is that if there are a bunch of events, A1 through AN, and they're mutually exclusive. So what that means is that they do not overlap at all. So the probability of A1 and A2 is 0, the probability of A2 and A3 is 0, and all combinations of probability of them overlapping is 0. And they have this other property that if you sum up their probabilities, it adds up to 1. And what that means is that they don't overlap and they completely cover the instance space. So there's nothing that happens that doesn't hit one of the A's, and there's nothing that happens that hits more than one of the A's. So if there is some other event B, you could find out the probability of B by summing up how much it overlaps with each of these A events, which are mutually exclusive, and add up to 1, kind of by just saying, well, look, the whole space is covered by those, and B has to intersect multiple of them, and let's just add up the ands of all those intersects, and that would work out to equaling B. So in this little example, we have A1, A2, and A3, which is everything that's not in A1 or A2. So it's kind of like the square with those two little circles cut out. Then you have some other event B, and so B is the part of B that intersects with A3, plus the part of B that intersects with A2, plus the part of B that intersects with A1, and that's exactly what that summation says there. So that's how you can recover B, or, manipulate some of these probabilities to get things that you need. Are you ready? Because we're ready to see Bayes' theorem. And we start from the product rule from the previous slide. And remember that product rule says the probability of A and B is equal to the probability of A given B times the probability of B, and it's also equal to the probability of B given A times the probability of A. So let's just start from that and do a little manipulation and come up with something that is surprisingly simple and surprisingly useful, because we can drop off that first part, the probability of A and B, because those are all equalities. So now we have this, and then one simple division. We divide both sides by probability of B, and we end up with this. And this is something that you should memorize. And also, we'll see on the next slide or two kind of how to use it. Because I don't want you going to a machine learning interview and saying, I took a machine learning course, and they say, okay, let's get started, write Bayes' theorem on the board. And you're like, well, I kind of only sort of paid attention in my machine learning course. Now, but this is the type of thing, and the application of this, they are the type of thing that are used in interviews commonly. It's a very useful tool, although you may never use it in practice. It's just a good thing to know. Kind of one of those rites of passage. Okay, so what is this for? Now, here's a common type of problem that we have in the world today. Maybe 2020 makes this even a little bit more important than this was the last time I taught this. COVID. Terrible, 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 terrible. But let's read this example and we'll work through this and we'll see how Bayes' theorem can be used to much better understand the underlying system and what's going on, and give you great ways to interpret observations that aren't intuitively clear. Like your just intuitive thought process of what an observation can mean can be quite wrong. So this is about a poor patient who goes into the lab and gets a cancer test. And this little word problem talks about the situation and the information about that cancer test. So a patient takes the cancer test and the results come back positive. Not good. But now we got to say, well, what does this mean, doctor? Doctor, what does this mean? The test returns a correct positive result in 98% of cases. 98% of the cases, it's a correct positive. So that sounds pretty bad for the patient already. And a correct negative result in 97% of the cases. That means if you don't have it, it would say no 97% of the time. So looking at these numbers, these are high 90s, and you might say like, oh geez, the patient, poor patient. Furthermore, 0.008% of the entire population has this, or I think that's 0.8%, something like that, of the population has this particular cancer for this example. So, okay, well, what does it mean? So what we have all of these things that we just talked about, and what I want to know is, I just took this dang test. Do I have cancer or not? What is the true probability of having cancer given that I just got a positive test result? Let's think this through. So starting out, we're going to need to figure out what's the underlying just probability of cancer. And that comes, we can read that right out of the word problem, and we can draw it on our little graph here. And so 0.008. The next thing, what's the probability of not cancer? That's just, those two things are going to add up to 1. One of the theorems I talked about probably is the reason that that's true. The next thing is, what's the probability of plus given cancer? Again, we can read that. And the probability of minus given cancer would be, again, these two things are going to add up to 1. So what do we have next? We have the probability of minus given not cancer. And that also is just written right here. So we can just read that over there, and then we again do the same trick. Something's got to add up to 1. So those two things there. So now we have all of this information, all those probabilities figured out. How are we going to get the probability of cancer given that we just had our positive test? I'll bet you use Bayes' theorem. So if we look at the form of this, the probability of A given B equals the probability B given A times the probability of A times the probability of B. I'm just saying it again, or divided by the probability of B. I'm saying it again because you gotta remember it. Now we can substitute in the variables that we're dealing with in this problem for A and B. And we could put in cancer for A and positive test for B. All right, that's good. Now we have a whole bunch of interesting numbers over here. Let's start drawing some of those into our formula and see how far we get. Well, we know this, we know that. We don't yet know the probability of plus. So how are we going to calculate the probability of plus? We can use the theorem of total probability, because we have the probability of plus given cancer times the probability of cancer, the probability of plus given not cancer times the probability of not cancer. And so that's just, you just got to see that one of those math trick things. We can read those numbers off of the table. And the probability of plus is this 3.7%. So now we can fill in the probability of plus, and we can do our multiplication and our division, and we can see, is it good news, is it bad news? Survey says Well, it's pretty good news. It says the probability of having cancer given that the test is positive is just 20%. But 90 and 90, what's going on here? So the next step that we can take is to be like, well, we don't just need to use plus and cancer. We can put a more general framework of the machine learning that we've been doing throughout the first lectures of this course. And we could say, what's the probability of y given that I have a particular feature vector? And, this feature vector could include the fact that there's a positive test, but it could also include other facts, like that you have a family history of this particular cancer, that you have specific other risk factors, that you have some actual symptoms that are commonly associated with this cancer. And then given all this additional information along with the positive test, that's when you would start to see, that you're getting closer to this 98%, when the doctor does the work up front to weed out people where the test really probably couldn't be a positive, and only apply it to the people where like, ooh, yeah, this person might need that test. Okay, so this thought process right here is what's going to lead us to the naive Bayes algorithm. Okay, now we got the naive Bayes algorithm. We're going to discuss how this Bayes theorem and the concepts that we've been learning can get us to this very simple generative machine learning algorithm. And here's a form of kind of what we'd like to do in some sense. This is a classification algorithm. I probably should have the y hat there, where we say y hat is the maximum among all possible class values, label values, y possibilities of this concept, which came from the Bayes theorem. And remember, this was probability of y given x is equal to this for any particular value of y. And then we could say, well, let's estimate the probability of every possible value of y, and in a classification sense, return the maximum of those. So what does that mean? Let's take this and go one step further. We, for any particular classification task, the actual x doesn't matter, because you're just comparing the possible class labels for that particular sample. You don't need to know how likely that sample is to figure out which class label has the highest probability, because this will be the same for all of them. And that's convenient, because trying to figure out how to calculate the probability distribution of all possible x's can be a pretty complicated task. A lot of parameters in that model, because of the way, like I talked about the curse of dimensionality, how as you add on more and more features, things start to grow exponentially. But we don't need to do that in order to use the naive Bayes algorithm to make classifications. But when we throw this away, we lose the kind of like calibrated probabilistic interpretation, but that's okay for what we're trying to do here. And so now after we drop that p of x off, we're left with this. And so, I'll just say one more time what this is that you look at each possible value of y, and you calculate this thing that's correlated or, related to the probability of y having that value, and you take the maximum one, and that's your prediction. Okay, that's good. Now let's take one more step. In order to calculate this thing here, what are you going to have to do? You're going to look at the training data, and you're going to use the training data to estimate this sort of like probability relationship. So for each possible value of y, because it's conditioned on the values of y, so you're going to have to bifurcate your counts, one for each possible value of y. You record the number of times each possible training example occurs with that y in the training data. So you have to have a table where the first index is the value of y. The second index is every possible instance that is allowed by your instance space. And then for each of those, you have to keep a counter. That doesn't sound very likely to work. But if you could do that, if the instance space was small enough, you just have like a small number of x's and you can allocate enough memory to keep all those counters, then you would estimate this probability as the number of times that the x that you're trying to estimate the y for occurred with the y divided by the total number of times that y occurred. So when that y happens, 20% of the time, that x was the x that was associated with it, or 0.02% of the time, that particular instance was the instance that was associated with it in your training data. These are all just, all these probabilities, you're just reading them out of your training data. But, as we said, this won't scale. If, anything beyond just the simplest possible couple dimensions, you're just not going to be able to keep the counts that you need to record those probabilities to do the estimation, to use this model to make discriminative predictions of the possible value of y. And so this is why Bayes is naive, because, right, but there's you make an independence assumption. And so what independence assumptions allow you to do is to say, I don't need to keep all this joint information about how all the different feature vectors happen together, all the possible combinations of these exponential many things. I can make an assumption that none of them depend on each other. And then the counters we're going to need to keep for this are going to be much, much fewer and much, much easier to manage. So if we assume that each xi is independent of the others given a particular class label, a particular value of y, and then we have, for the counters we need to keep, for each value of y, so each possible prediction, in the spam case that would be 0 and 1, for each value of xi, so that's a particular x that we're talking about, so the first one would be like the presence or absence of a particular word, the second one would be a presence or absence of another word. So for each value of y, spam or not spam, for each value of xi, either the word is there or not, record the number of times xi had that value. So the counter is, instead of being all possible combinations of x, for each y, for each x, for each possible value of x, you keep the counter. Much, much more manageable. And then you estimate this probability of a particular sample given the class label, which is, what am I going to try to predict for a particular instance at runtime, as just iterate over all of its features and multiply the probability of that feature having that value in conjunction with the particular label. So you'd say, the probability that if this were spam, x1 would be 1, because, plus or times the probability if this were spam, x2 would be 0, times the probability if this were spam, xy, blah, 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 blah. Then you do that for spam and not spam, and you get those products, and then you take whichever label is higher. So that's it written out. That comes from there. Just moved over there. I did a little switcheroo. This comes from the independence assumption, and that is an approximation to that based on the independence assumption. And then the way you estimate this is written right there. With the appropriate counts. But don't worry, now we've seen this, now we're going to go through an example and click the numbers, and I think, different brains get at this stuff in different ways. Okay, now let's work through this naive Bayes thing with this particular example, and here's the training set that we're going to work with. Now we want to produce a model that lets us use naive Bayes to predict the value of y given these features x1 and x2. So what are the parameters of that model? Those are the counters that we talked about on the previous slide. So for each value of y, for each x, and each possible value of that x, we have to count the number of times that occurred in the training data. Now let's walk through one or maybe two just to see. So when y equals 0, the probability that x1 has the value of 0. So here's an example that has that property. Y is 0, x1 is 0. Here's another one that has that property. Here's another one that has that property. Here's another one that has that property. So 4 times out of how many zeros are there? There's 1, 2, 3, 4, 5, 6. So 4 out of 6 times when y is 0, x1 has the value 0. And then, you could do simple math, or you could go and count and say, well, then x1 would have the value of 1 2 out of 6 times, because those are the only possibilities. I think you can see now how to go and fill out this table. I think it's kind of like, yeah, okay, I get it. And then the other thing that you need to keep account of is the distribution of these labels, the class labels, where y equals 0 happens 6 times and y equals 1 happens 4 times. And you just count that off of there. Okay, so there are the parameters of the model. And remember, we're going to probably do something like additive smoothing we talked about. And on the next slide, I'm going to go through that in a little bit more detail. But just, I wanted to say this here while we're looking at all of this. So we might not take those exact counts directly. We may take some version that's slightly smooth to avoid numerical problems, and for a reason we're going to talk about in a second. So how do we do this? We have to look at the model, and this is the formula we ended up with at the very end of the last slide. And we'd have to say, for each y, each possible y, we're going to calculate this, given that these are the feature values. So that would work out as, for y equals 1 and for y equals 0, we'll say the probability that y equals 1 times the probability that x1 equals 0, given that y equals 1, times the probability that x2 equals 0, given that y equals 1. And, these zeros come from here. Those are why we're choosing to calculate those particular probabilities. So then you could just look those numbers up in your table, and here we go. Oops, the table for 1 is on the bottom side. But anyway, it doesn't matter. That's where you would draw those numbers from, and then you could fill those in, and you would say, your estimate here is 0.025 of the class label being 1. Then you do a similar thing for the possibility that the class label is 0, and you would take that, and you would take those things from up there, and there's the number, and so it's 0.13. 0.13 is way, way, way larger than 0.025. So to use naive Bayes with these parameters to get a prediction for this instance, or this x, or this training or testing instance, you would predict, in that case, y hat equals 0. All right, there you go. Very simple model. There's not really an optimization phase. There's more of just a count your training data up phase, and then ship the parameters and go. When you are using data to make estimates, there's 2 philosophical approaches for doing it. And one of them is that you estimate the probability that you're trying to estimate from observations of data. You look at the data, whatever the data is telling you, you use that, you go, that's my estimate, let's go. The other approach is to estimate the probability based on the data, but also based on your prior knowledge of how the world works, some form of prior assumptions. And these 2 estimation techniques are called, on the left, we have the maximum likelihood estimation. That is, what's the most likely estimation given the data that I have? And on the right, we have this maximum a posteriori. You would not believe how many times I had to say that to get that right. The map, I'll say map from now on because I'm never doing that again. The map estimate, which is combining the data with your prior assumption. So how does the data affect your prior assumption, and use that as the estimate that you come out with on the other side. And this side here on the right is Bayesian. So if you say I'm a Bayesian statistician, you're always thinking about prior assumptions and map estimates. And if you're a frequentist, you'd just be like, yeah, I mean, you can do all that, but I'm just going to look at the data, and this would be frequentist. So let's go through a few steps of how these people might come to estimates differently for a very common case. And that is, if you flip a coin a bunch of times and you see a certain number of heads, the probability of heads is the number of heads you've seen divided by the number of times you flip the coin. This is very similar to what we talked about bounds and all that stuff in the past. So that is where we start, but now let's look through an example and say, let's say we flip a coin 50 times and we see 22 heads. What is the probability of the next flip of that coin being heads? And if you're a frequentist, you would do a maximum likelihood estimation, and you would say that that probability is 44%. Okay, maybe that's true. Well, what if we did another example? And we said, well, okay, let's flip the coin 3 times and you see a head 1 time. What's the probability that that coin is going to be heads? Now you're getting a little bit like, 3 flips of the coin, and I'm going to say 33%. And remember that when we talked about bounds and all of that stuff, we would just know that, hey, with this very small n, the variance of the estimate is going to be quite high. So you shouldn't just say 33%. You should put like some error bars on it, right? Like you wouldn't just say 33%. You'd say 30, here's the range of what the probability of heads is. Because, right, like that's important stuff. Remember that. But the point is that your estimate, your most likely estimate of what the answer is, aligns with your estimate from sampling the data. So the data says 33%, you say 33%, but you just say, hey, there's some error bounds. Now, if you flip a coin 0 times and see 0 heads, what's the probability it comes up head? Well, as a complete frequentist, you really don't know, right? Unless you bring some prior assumption to it. I mean, you could say like, well, it's pretty hard to create a coin that would only come up heads. Like that doesn't seem to make sense to me. So it must not be 100%, but I don't know. So now, now you're getting into this world of being a little bit Bayesian and bringing your prior understanding of the way the world works to this task of estimating these values that you might want to talk about. So one way to do this is this additive smoothing. This is also called M estimates. But you have a prior, and the prior is represented by a P, which is, here's the probability I think this coin will come up heads, and an M, which is, and this is how much I think my prior is correct. This is how certain I am in my prior. This is how much data you'd need to show me to the contrary to get me to give up my prior. So where over here you would just say the number of heads divided by the number of flips, in the map side you would say the number of heads plus my expectation of what the distribution of heads will be times the strength of my conviction. And so this M, you could think about it as an equivalent sample size. So if M is like 10, you would say, I have 10 samples of prior certainty that this coin is a particular type of coin. And if you show me 10 samples of data that say something else, those will balance and we'll have, then we'll be on even footing. But that's my the strength of my conviction. So if we said we have a prior with strength 10, equivalent sample size of 10, that any coin you show me is a fair coin. Like, I don't think I've ever really seen a biased coin. I don't think that's a real thing. Maybe my M would be higher. But for this example, we'll use an M of 10. Then in this case, where we flip a coin 50 times and see 22 heads, we don't return an estimate which is the maximum likelihood estimate from the data. We return an estimate that combines our prior with what we see in the data. And so now we return 45%. Because, you did flip the coin kind of a lot of times, and it's starting to look like, it's not a totally fair coin, but I still think it's probably a fair coin, so I'm going to weight it back towards that 50% number. In the case when we flip the coin only 3 times, you could see that even though in the data it was coming up at a 33%, because our prior is, quite a bit stronger than 3 coin tosses, we're going to return an estimate and say, no, we think it's a 46% would be our estimate of the probability of heads of that coin. And then in this 0-0 case, there would be no data, so you would simply return your prior, and which is like, this is what I thought, that coin is fair. The person holding the coin is fair, everything's fair, it's 50-50. We don't need to look at any data or whatever. And all of this is a long-winded way to say that when we're looking at statistics, it's often good to bring a small prior. And that's the justification of doing this additive sampling. That's why we would do that when we were calculating the mutual information. We would have a small uniform prior a small prior that the data is really uniform, that one way or the other isn't the thing. And in this case, this particular example, we would have a small prior that the coin is fair. Or when we're calculating all those statistics for naive Bayes, we would have a small prior that everything is uniform. And just in case, it's not in the training data, then we can rely on our prior and still make estimates without having seen the specific case ever occurring. For example, if you have a training set where every x3 has the value of 1, you never see x3 of 0 in your training data. I mean, maybe your training data, that's not great, but that could happen, I guess, but it's not great. But then if at runtime you do happen to see a value that wasn't in your training data, you bring a slight prior to the model when you're learning the model's parameters, and you're able to make a prediction for that anyway. All right, so that is naive Bayes. That is some basics of probability and a little bit about the thought between Bayesian and frequentist statistics. Oh, did you guess which one I am? I won't tell you. I don't want to get in trouble. But naive Bayes summary. The structure of naive Bayes is a very simple probabilistic model that all the xi's are independent of each other. So the structure and the parameters are the counts for each possible value of y, how many times that occurred, and then for each value of y and each possible value of x, how many times those things occurred together, each y with each value of x. The loss is nothing. You just estimate the parameters from the training data, use your map estimate with a small prior, and that's all you do. There's no optimization, there's nothing, and in fact, the optimization phase here, none. You just look at the data and count it up, and maybe use a little bit of prior knowledge and an independence assumption. So that is naive Bayes. What's it good for? It's good for, right? Like it's good for an introduction to generative modeling. It's good for an introduction to Bayesian thought. It's good for setting you up to see why this approach to thinking about data modeling can be quite valuable. But I would have to also balance with that. In practice, it's don't use it. Do not use it. Maybe like I've seen it used as baselines in research papers, something along those lines. But if you go into the room and say, hey, use naive Bayes, like I said, no. All right, well, there you go. And I hope you enjoyed this lecture, and I'll see you next time.